There are 100 billion stars in our galaxy, the Milky Way, and there are 100 billion galaxies. Those stars, which are of an average size like our Sun, will live for about 10 billion years, fueled by continuous nuclear fusion in its core, converting hydrogen into helium. At the end of their lifespan, when all of the hydrogen is used up, helium fuses into carbon, releasing prodigious energy and causing the star to become hundreds of times larger, a red giant. Gravity will finally cause the red giant to collapse and violently throw off its outer layers of matter, leaving only a white-hot remnant core called a white dwarf. There are billions of such white dwarfs, and they too will eventually burn out and go dark. The outer layers of gas that had encased it when it was a star have been blown off, and ever since, the material has been expanding far out into space. This ring may appear to be two-dimensional, but it is actually a sphere, because stars typically throw off their matter outwards in all directions. This is called the Helix Nebula. Nebula simply meaning a huge cloud of gas and dust. The nebula is exploding outward, unchecked by the gravitational restraint of any nearby massive object. A closer look at a portion of the nebula in detail will reveal its cosmic magnitude and the astounding speed at which it's traveling. This gas and dust is racing outward at some 18 miles per second. That's 60,000 miles an hour. The actual size of these occasional round, droplet-shaped patches of cloud is immense. Each one is twice the size of our entire solar system, but the amount of matter in them is extremely sparse. The scarcity of matter in a nebula approaches that found in a perfect vacuum. The length of the comet-like tails left by these racing globular parts of the nebula are up to 1,000 times longer than the distance from Earth to the Sun. Another white dwarf is still closely surrounded by a thick layer of gas it had violently cast off. The explosion had happened only a few thousand years ago. Images over time of the enormous Cat's Eye Nebula have recorded the startling velocity at which such a vast cloud of gas and dust can expand. 3 years after this first image was taken, this second one was recorded. In the cosmic scale of distances, this seemingly slight expansion has actually increased its diameter by several billion more miles in just 3 years. When the dying star throws off its outer shell, it loses half of its mass. But the white dwarf that remains is far less than half its original size. It was about this big. Gravity has crushed the white dwarf's atoms, squeezing electrons, protons, and neutrons together. 1 square inch of white dwarf matter weighs about 6 tons. It has been squeezed down to a size only a little larger than that of Earth. The various colors which are emitted by the atoms of different elements in a nebula are distinctive and identifying. The color green indicates hydrogen. Red is an indicator for the presence of nitrogen. And blue shows that oxygen is present in a nebula. Nebulae come in many shapes and sizes and in various colors, that is, consisting of various chemical elements. Although these nebulae are in fact the remnants of stars, not planets, they are known as planetary nebulae. This inaccurate term stems from the time when telescopes could not deliver particularly sharp images, and astronomers observing stars mistakenly thought they were seeing planets, but the term stuck and is still used today. The further the nebula expands, the thinner and more transparent it becomes, until eventually all that's left is only the white dwarf by itself. Here, several white dwarfs are close to one another. They are cooling off as they make their way through the infinite distances of the galaxy. Eventually, they will lose all heat and go dark. So, red giants and white dwarfs with their planetary nebulae are therefore not different types of stars, but different stages in the life of a dying star of an average size. But what then is the explanation for the many other types of stars which have been observed? In the 1960s, astronomers discovered one of the most curious objects in the sky. It was a faint star located in the center of the so-called Crab Nebula. And it didn't radiate light continuously, but rather flashed on and off in rapid intervals, many times a second. Its pulsing radiation was so precise that at first scientists believed that they had stumbled across messages from extraterrestrial life on a star. But they soon came to realize that it was the star itself that was the source of the pulsating light. They observed that the pulses did not radiate from the whole star, but as cones of light emitted from the poles. And each time a cone of light swept across the Earth, we saw a pulse. And that gave the star its name, a pulsar. 30 pulses a second means that the star rotates 30 times a second, and that the enormous centrifugal force doesn't tear the star apart indicates that its gravity and density must be extraordinary. Interestingly, physicists had already calculated and predicted such a bizarre object decades earlier. They postulated that the life cycle of a star is dominated by a single factor: gravity. Gravity is significant at the birth of a star. Stars are born in giant nebulae when, under the pull of gravity, its gases begin to coalesce in areas here and there. It is the beginning of a process which will last several million years, and during which ever more matter is collected until eventually a sphere of gas begins to take form. As mass increases, so does gravity. It compresses the gas at the center of the embryonic star, and that heats it up until it becomes incandescent. Once the interior temperature reaches 15 million degrees centigrade, the nuclear fusion process begins, with hydrogen being converted into helium, and a star is born. Its mass will dictate how a star will eventually die. There are giant stars with a circumference larger than Earth's orbit around the Sun, and whose gravitational pressure eventually becomes so great, and whose core is compressed to such a tiny volume that their inner core temperature soars up to several billion degrees centigrade. Now the atomic nuclei are moving so rapidly that they overcome the mutually repulsive forces of their protons and electrons, which had kept them apart, and they fuse. Increasingly complex and heavier nuclei are fusing, creating new and heavier elements. Under immense gravitational pressure, the core is further squeezed and atoms themselves are torn apart. Only neutrons remain and become so tightly packed that the core collapses. The catastrophic implosion releases a shock wave that tears the star to pieces in a spectacular explosion, a supernova, the most brilliant event known in the universe. The core remaining is so dense that 1 teaspoon of it weighs 3 billion tons, and 30 rotations per second can't tear it apart. It has become a pulsar, or neutron star. The pulsar in the Crab Nebula is just such a neutron star. It exploded in the year 1054, as we have discovered from the records of ancient Chinese astronomers. Since that time, its planetary nebula has been expanding and has now reached the size of several light years across. Planetary nebulae expand until their atoms become so thinly spread out that we can no longer see them. Yet even in the vacuum-like space between stars, each cubic yard still contains millions of atoms and molecules, dark and invisible. Recent observations verify that the mass of a star will determine what remains when it dies. Data tell us that when a dying star finally collapses, the greater its mass, the greater is the force of gravity that will squeeze its core. As we have seen, medium-sized stars like our Sun will leave behind a dense white dwarf like this, with a diameter of about 8,000 miles, Earth-size, but weighing from 0.5 to 1.4 solar masses, one solar mass being the mass of our Sun. A giant star, 10 to 20 times the mass of our Sun, leaves behind a very dense pulsar or neutron star with a diameter of only about 9 miles, yet weighing 1.4 to 3 solar masses. And there are gigantic stars, 20 to 100 times the Sun's mass, whose remnant core diameter is merely about 4 miles, but weighs more than 3 solar masses. Their matter is so dense that their enormous gravity doesn't even allow light to escape. Without any light escaping, the core is invisible. A black hole. Whatever crosses the defining circumference of a black hole, called an event horizon, disappears forever. In its interior, time and space cease to exist. Stars, which not so long ago seemed to be eternal, we now know to be mortal. Stars in our galaxy, as in all others, are made of elements in continuous and intense chemical reactions which measure their lifespan and determine their fate. We are now able to observe them in every stage of their life, from birth to death. As immense, profound, and mysterious as the universe is, it is every bit as astounding that an intelligent life form on one lonely planet is just beginning to comprehend it.